In this video, we will demonstrate how to divide an air conditioning diagnostic problem in two by using an electronically controlled variable displacement compressor driver tool. Many modern vehicles now use a computer-controlled variable displacement compressor. Performance issues associated with these compressors can be difficult to diagnose. This tool can quickly help you determine if an air conditioning performance issue is related to the compressor and basic refrigeration circuit, or if the problem is related to the computer control system. In short, we can divide the problem in two and halve our diagnostic time. The tool has three testing modes: resistance check, normal, and manual. We can check the resistance of the displacement control solenoid, monitor the actual command being sent by the computer to the solenoid, and most importantly, use the tool to manually function test the compressor, completely independent of the computer. It is available with over 40 individually numbered custom pigtails to fit the ECV solenoid and vehicle harness on virtually every vehicle on the road today. But to really understand the power and value of this tool, we need to understand how a variable displacement compressor actually works and the difficulties associated with successfully diagnosing them. Modern, smaller capacity engines are especially sensitive to transient loads, such as compressor cycling. Early compressors were fixed displacement designs. The only way to control the output of a fixed displacement compressor is to turn it either on or off. This is very inefficient. Idle quality, emissions, and fuel economy are all adversely affected as the compressor cycles on and off. The solution for these problems is to use a variable displacement compressor. The pumping displacement of a variable displacement compressor can be varied smoothly and seamlessly to precisely match the changing heat load on the system. This avoids the necessity to constantly cycle the compressor on and off. A variable displacement compressor uses only the minimum energy necessary to meet the demand on the system. The result is improved fuel economy, reduced emissions, and a smoother idle. Today, over 70% of new vehicles are equipped with an electronically controlled variable displacement compressor, usually referred to as an ECV compressor. Compressor pumping capacity is controlled by changing the stroke of the pistons, which are attached to a variable angle swash plate. Changing the angle of the swash plate changes the stroke of the pistons, as you can see in this cutaway demonstration. The angle of the swash plate is controlled by modulating the crankcase pressure with a duty cycle control solenoid in the rear head of the compressor. Increasing the duty cycle lowers crankcase pressure, which increases compressor output, and vice versa. Here on this ECV compressor test station, the three pressure gauges from left to right along the bottom represent suction pressure, crankcase pressure, and high side pressure. As the duty cycle command increases, high side pressure starts to increase, while suction and especially crankcase pressure start to fall. The computer takes account of many inputs to fine-tune compressor displacement for maximum efficiency, including evaporator temperature, system pressures, ambient and cabin temperatures, compressor and engine speed, driver habits, and so on. Note also that through the special translucent crankcase, the angle of the swash plate changes as duty cycle increases and crankcase pressure drops. So let's look at some of the difficulties associated with diagnosing these compressors and how the ECV compressor driver tool can help simplify our diagnosis. First, there are two basic versions of ECV compressors, which can sometimes lead to confusion. Most early versions were clutchless. They do not have a conventional electric clutch. This means that the compressor shaft turns all the time, even when the AC is off and it's 40 below. To the naked eye, the compressor appears to be always engaged. More recently, some ECV compressors now have a conventional clutch. For these compressors to work, the control solenoid must be receiving a duty cycle command and the clutch must be engaged. Here is a typical scenario where misdiagnosis of these compressors often occurs. The customer complains that the air conditioning is not working. The compressor appears to be engaged, yet both high and low side pressures are almost equal. High side pressure is abnormally low, and low side pressure is abnormally high. Traditionally, this would indicate a failed compressor that cannot pump. And so the shop replaces the compressor, only to find that nothing has changed. Of course, for this compressor to work, the computer must be sending a duty cycle command to the displacement control solenoid. This is where the ECV compressor driver tool can prevent a misdiagnosis. So let's hook up the tool and see how we would diagnose a vehicle with an actual problem. The tool has 3 lead connections. We will connect one lead set to the battery to power up the tool. We recommend always connecting the ground lead of the tool first to avoid accidental damage. Next, we will disconnect the vehicle harness from the compressor solenoid and select the appropriate male and female pigtails from the kit to connect the other 2 lead sets to the compressor and the vehicle harness. Scanning the QR code on the tool instruction sheet takes you directly to an online application guide to select the appropriate pigtails for the particular vehicle. The guide can also be downloaded for offline use. We are now ready to start testing. Pressing any button on the tool powers it up. The tool defaults to normal mode on startup. It's good practice to always start by checking solenoid resistance. This is easily done by pressing the resistance check button on the tool. Here the resistance is around 12 ohms. Many ECV solenoids are in the 10 to 14 ohm range. Obviously, if the resistance is out of range, we know there is a problem right from the get-go. Next, we will set the AC system to max cool. With the tool in normal mode, the display indicates the actual duty cycle command being sent from the computer to the compressor solenoid. In normal mode, the tool does not play an active role in the circuit. It simply displays the duty cycle command being sent from the computer to the solenoid. If we vary the heat load on the system by raising or lowering blower speed or switching between recirc and fresh air, the duty cycle command should change as the system responds. On a hot, humid summer day, the duty cycle command will be high, in the 80 to 100% range. If the duty cycle command is high, but high side pressure is abnormally low and low side pressure is abnormally high, most likely there is a problem with the compressor itself. If the duty cycle command is higher or lower than we would expect, then we would review scan data for out-of-range inputs. On the other hand, if the duty cycle command is 0, then we would need to investigate why the computer is not sending a command to the solenoid. Perhaps the engine or transmission are overheating, or system head pressure is too high, for example. Notice how the tool made it fast and easy to determine which area of the system needs additional testing. Obviously, if the command is 0, we know that there is a computer-related issue that will need to be diagnosed and repaired. However, we would still like to confirm that the compressor is fully functional and that the basic refrigeration system works before talking to the customer. So, by switching the tool to manual mode, we can take direct control of compressor pumping displacement and test the compressor and basic refrigeration circuit completely independently of the vehicle's computer. As we manually increase the duty cycle command, high side pressure should start to increase and low side pressure should drop. If we reduce the duty cycle command, pressures should start to reverse. Note, while the bidirectional testing function on a scan tool may provide some capability to test an ECV compressor, in our experience it often leaves a lot to be desired. On some clutchless systems that do not actually have a compressor clutch relay, the scan tool test function may display a confusing and misleading option to cycle the magnetic clutch relay on and off. And on other systems, the scan tool may only allow compressor testing with the engine off. Not much practical use at all. To sum up, the ECV compressor driver tool can significantly shorten your diagnostic day. It enables you to check 3 separate areas of the system very quickly and easily: the resistance of the ECV solenoid, the command from the computer to the solenoid, and to function test the compressor completely separate from the computer. It has a comprehensive library of custom pigtails for virtually every application and an online-offline pigtail application guide. Thank you for watching.